going to be meters per second because the two values, the two x values on top are meters, and then the values on bottom are seconds, so it's going to be literally meters divided by seconds, which is a velocity. And so I'm not going to take the time to walk you through just plugging the values in and figuring out the answers, so I'm just going to write them in right now. Pause the video again. Just because I think this is easy enough for you guys to understand without me really showing you. If you do need a little more explanation, just ask for it later on. But for now, I'm just going to pause and fill in the stuff. Alrighty, and so these are the filled in values. Hopefully you got all the right answers. And actually, if you were following along with what I was doing, and we're also looking at your own paper, you should have noticed that I actually made a mistake. When I had written down all the givens, I accidentally had this as the wrong value. So again, hope that you caught that. If not, no big deal, but I do make mistakes. So we're going to move on to the next problem now, number 4. So before we even get started, we need to draw the sketch. So it's supposed to be of a baseball pitcher throwing a fastball to the catcher 13.7 meters away. So what we're going to do is we're just going to draw our two people. We're really going into art here. So we've got our pitcher, let's call him P, and we've got our catcher. And now he's throwing the ball toward the catcher, so we're going to make that the positive direction. And the velocity of the ball is in that direction. And the overall distance, which is the change in x. And now on sketches, we're not supposed to put numeric values into it. It's just supposed to have the symbols for it. So I'm not going to actually fill that in. So we've got in our givens, we have the change in x, which is equal to 13.7 meters. Now the reason that it's positive is because the positive direction is pointing toward the catcher. If we had made the positive direction that way, then the change in x would be negative. That's just something to keep in mind in the future while you're doing these problems. Also, we know that the velocity of the ball is equal to 150 kilometers per hour. So the unknown, or the thing that it tells us to find, is the amount of time that it takes for the ball to get from the pitcher to the catcher. So for our equation, this is pretty much going to be similar to number 2 again. We've got our base equation, except this time, instead of finding the velocity, we're going to be finding the change in time. So once again, the x initial is 0, so just ignore that. And we're just going to divide by the velocity. So we're going to end up with the total distance over the velocity is equal to the change in time, or the amount of time that it takes for the ball to get to the catcher. So for our substitution, we have 13.7 meters over 150 kilometers per hour. Now this makes us run into a problem. The units are not the same. We have meters up here and kilometers down here. So what you're going to want to do is, since I don't want to mess with converting the decimal and everything, I'm going to change it so that it is meters. It is in meters. But also, the problem is we're in hours, and the ball really isn't going to take hours to get from the pitcher to the catcher. So we're going to have to convert both of those into meters per second. So what we're going to do, this is something that we did in chemistry, I remember, in order to find different values of things. Forget exactly what it was for. but you've got your 150 kilometers per hour, and then for every 1 kilometer there are 1,000 meters. So you'd be multiplying this. So you'd have 150 times 1,000. And then for every 1 hour there are 60 minutes. And for every 1 minute there are 60 seconds. So if you understand what I did just there, I just broke down the hours into seconds by dividing it by 60 and then by 60 again. So in the end, the final velocity should be 41.6 meters per second. So what you do is, it's just a big multiplication and division problem. So if you, instead of this grid being here, you imagine multiplication signs and division signs, the stuff on top is multiplied, the stuff on bottom you divide. And so you can use that and plug it back into the substitution equation. So you have 13.7 meters over 41.6 meters per second. And because of the magic of fractions and everything, the 2 meters cancel out and the seconds go to the top, just because of that's what happens when you multiply the fractions out and everything. So the final units that you're going for is seconds, because you're trying to find the time. And so in the end, what you find for the solution is 0.329 seconds, if I can spell. Or if you just go by the rounding that they have, you have 0.33 seconds as your final answer. Hope it didn't throw too many of you guys off by this multiplication thing. But honestly, we won't be using it all that much. I think we use it for the next problem. But throughout the entire year of physics, you don't have to use that all that much. Alright, so now we're going to do problem number 5. Okay, for problem number 5, we are told that the Olympic record for the marathon is 2 hours, 9 minutes, and 21 seconds. Then we're also given the average speed of the runner who got this record, and so we're supposed to find the distance of the marathon. So, first things first, we're going to make our little sketch. So we've got a little person at our X initial, and then we've got him finishing the race. We'll have his arms up because he's celebrating, for the X final. So overall, we've got the change in X, which we have to find. So we're going to say that the positive direction is that way, and that his velocity is that way. And I know it seems like we're doing that for every single problem, that it might seem pointless, but later on in the year, when you've got multiple velocities going in different directions, you're going to want to have that. So, for our givens, we have his X initial, which is equal to 0 meters, and we have his time. Now, the thing that we're going to need to do is convert his time into seconds. And the reason we're going to do that is because his velocity, which was 5.436 meters per second, is just that, in meters per second. So what we're going to do is we're going to use the same kind of table format that we used in the last problem. So we're going to convert 2 hours into seconds. So for every 1 hour, there are 60 minutes, and for every 1 minute, there are 60 seconds. So then what we are going to do is convert the minutes into seconds. So you've got 9 minutes, and once again, for every 1 minute there are 60 seconds. So you're going to multiply that together, multiply those together, add them together, and add them to the seconds. So the actual time that he spent was 7,761 seconds, if I did my math right. Yes, that should be correct. Okay, so next what we're going to do is we've got to find our unknown, which is change in x. So for the equation, same old, x initial plus v time. Now sometimes I'll write the v average, sometimes I'll just write a t. It's all one and the same. You don't really need to change any of that stuff. It's just the way I'm writing it sometimes. So x initial is equal to 0, so we can cross that out. And so for our substitution, because we're trying to find the x, we don't really need to change the problem at all. So his velocity is 5.436 meters per second times 7,761 seconds. And so you multiply those together, and what you get will not match the thing that they have as the solution, because next to the problem it should have the answer for most of your questions. And the answer that they have is 4.22 times 10 to the 4th meters. If you were to actually multiply it out, however, what you would get is something a lot uglier. You would get 42,188.796. So what they did is they put it into, as my physics teacher liked to call it, proper Plano pre-AP scientific notation. That's a mouthful. Basically what it is scientific notation where all you have is the first 3 digits, and then you would round, and you'd put the rest into scientific notation. For those of you who don't know exactly what scientific notation is, it is basically just the moving around of the decimal point, and so that's how you would get to the 4.22, because you would round the 8 up to make that 1 into a 2. Then what you would do is you would figure out how many places were between your new decimal point and its old place. And so if it moves forward, so if the decimal point were to move 1, 2, 3, 4 to right here, then you would put a positive 4 as the exponent on the 10. However, if the decimal point moved in the opposite direction, it wouldn't in this problem, but if it moved in the opposite direction, it would be times 10 to a negative number. So scientific notation is important for physics, but hopefully your teacher will have gone over that with you by now. Okay, so now we're going to move on to question number 6. Okay, in number 6, you're going to see how important having a positive direction labeled really is. To start off the problem, we have 2 runners. So we have runner A and we have runner B. And according to the problem, they're both moving toward a flagpole that is somewhere between them. So runner A is a certain distance from the flagpole, and runner B is a certain distance from the flagpole. And since both of their velocities are moving in opposite directions,